Welcome. In this video, we're going to talk about the one-way between subjects analysis of variance, or ANOVA for short. This is the introductory type of ANOVA that one would encounter. You should be aware that there are many different types of ANOVA, but this is the one that we'll cover in this basic statistics course. So one way implies that there's one independent variable. Between subjects implies that participants, a given participant would be in one level of that independent variable, but not multiple levels of the independent variable, as opposed to a within subjects or repeated measures design, where a participant would take part in each level of the independent variable. So in the end, we're comparing independent groups of people, much like the independent samples t-test applied to a between subjects design. One way between subjects analysis of variance applies to a between subjects design with a categorical independent variable and a interval ratio dependent variable. So for studies with more than two levels of the independent variable, we can't use the t-test. T-test basically compares two groups or two samples. So we won't be able to use the independent samples t-test. You might think, well, we could just do a bunch of t-tests, but that does create a problem because that would inflate the type 1 error. So the more tests that you do, let's say you're doing a research study, the more tests that you do in the research study, the greater the likelihood of making at least one type 1 error. So if we were comparing an independent variable that had 4 levels, you would need to test 6 t-tests to get all pairwise comparisons, and that would inflate the type 1 error. As you can see here, the number of independent hypothesis tests that you perform greatly increases the likelihood of making at least one type 1 error. And assuming we want to avoid that because we don't want to make errors, we want to take measures to make sure that we minimize the likelihood of making a type 1 error. So doing an ANOVA does that in a sense because it allows for a test that compares all of the means in the situation where there are more than two means to be compared. So we would use a one-way between subjects ANOVA when you have a between subjects design and the independent variable has 2 or more levels. It can be used with 2 levels. Most people would just use a t-test if there's 2 levels, but it could be used with 2 levels, like the independent samples t-test. So basically it would give you the same answer. So with 2 levels, the F ratio, which is the resultant statistic of the ANOVA, which we'll get to in a little bit, is equal to the t value squared. So they're essentially the same statistical test. As I said, the dependent variable should be interval ratio, or at least we're assuming that it's interval ratio. And ideally, samples are taken at random, or random assignment to conditions should be used. This is not always feasible, but that's ideally. And then also the homogeneity of variance assumption, which you might recall from the independent samples t-test, that still holds. So because we're going to pool the error variance into one error term, we would want to make sure that the variances, or the errors basically, within the subgroups, within the different levels of the independent variable, that they are similar in our samples, or at least not too dissimilar in our samples, and we would assume that they are the same in the population, although there's some corrections that can be applied if we do violate the assumption of homogeneity of variance. So you can just think of homogeneity of variance as being assuming equal variances in the groups in their respective populations. So to extend our soda example, let's say we wanted to throw another type of soda in the mix. So we're comparing American Coca-Cola, Mexican Coca-Cola, and I believe that's RC Cola, which you should generally avoid. And we're comparing them on some interval ratio scale of taste satisfaction. And for some reason, let's say we want to avoid carryover effects, and we want to avoid, just giving people too much soda. It's not good for you. So we'll randomly assign people to either drink the American Coca-Cola, the Mexican Coca-Cola, or the RC Cola, and then we would compare the means between the groups. Now, we'd need large enough groups in each condition to see if there's a difference and to ensure probabilistically similar groups. Remember, the purpose of random assignment is to kind of equalize the groups for whatever variables people are bringing in to our little taste test experiment. So the null hypothesis here is a little bit different than what we're used to. The null hypothesis will typically state that there are no differences between the population means in the group. So that we have since we have typically more than two groups that are being compared, the null hypothesis is saying that basically the means are all the same, they're all coming from the same population more or less. The alternative, however, says that there's at least one difference. So when we reject the null, we know there's at least one difference. Pairwise difference between the group means that we're comparing. There may actually be more than one difference, but if we reject a null, we can be relatively confident that there is at least one difference, at least on the basis of our results. So the null is that all the means are the same, and the alternative is typically that there is at least one difference. So the test statistic that we're going to use is no longer the t-distribution, it's the f-distribution. The f-distribution is a family of distributions based on two types of degrees of freedom. We can call them degrees of freedom effect or degrees of freedom error. Some books might call them degrees of freedom between and degrees of freedom within. But in any case, the shape of the distribution depends on the degrees of freedom. But still, we're dealing with the same concept in terms of the proportion of the area under the curve and comparing alpha to the proportion of the area under the curve beyond the f value that we obtain. Now, the thing about the f distribution is we don't have to worry about negative and positive values because for the ANOVA itself, the f value will not be negative. The lowest it can be is 0. 1 implies that there's basically the error variance is equal to the effect variance. So the f must be over 1 in order for there to be an effect, but usually it has to be a little bit or quite a bit over 1 in order for us to be able to say that we can reject the null and that the proportion of the area under the curve in the tail is small enough below alpha to reject a null hypothesis. So what's basically being done in an analysis of variance is we're partitioning the total variance. So you can think of the total variance, we'll think of it in terms of, actually let's think of it in terms of sums of squares. So there's sums of squares total, and that's the sum of squares that you're used to computing. That's basically the sum of all the squared deviations around what we'll call the grand mean. Now the grand mean is the mean of all the data ignoring the groups. So in our soda example, ignoring which soda group a person was assigned to, just calculating the sum of squares total, that will give us all the sum of squares, the total of the sum of squares for the ANOVA design. Sum of squares between, on the other hand, is the sum of the square deviations of the group means around the grand mean. So this is kind of like a raw measure of how much effect we have. So if the group means are deviating substantially from the grand mean, that might indicate that we have some evidence that there are differences between those means. However, we also need to take into account error, or what's sometimes also called sum of squares within. The sum of squares within is the sum of the square deviations of the individual scores within a group around their respective group means. So that's a way that we measure the error. So if the groups are pretty tightly bunched around their respective group means, then there will be less error. If the groups are spread out around their group means, then there will be more error or more sum of squares within. And these two, sum of squares between and sum of squares within, if they're calculated properly, will add up to sum of squares total. And in the end, what we'll do is we'll compute the F ratio, but there's a couple more steps which we'll get to in a second. But in the end, basically what we're going to do is compute the F ratio by taking the effect variance, which is based on sum of squares between, and divide it by the error variance, which is based on sum of squares within. And if there is sufficiently more effect variance than there is error variance, then the F ratio will be higher. There will be a lower proportion of the area under the curve in the tail. In other words, there will be a lower p-value. And if it's lower than our alpha, we'll be able to reject the null hypothesis and say that there is at least one difference between the groups. So here's, if you want to do this by hand, here's a fun way to do it by hand. You set up one of these things, which used to be quite prevalent in scientific papers, but those days I think are long gone. This is called an ANOVA table. And then in the ANOVA table, you compute the sum of squares between, you compute the sum of squares within. Here's the computational formula. It looks a little daunting, but if you take it piece by piece, you could actually do this by hand. And in a subsequent video, there's an example of how to do this by hand. You wouldn't use the conceptual formulas to do this because it would take forever. It takes long enough just to do it by hand using these computational formulas. But basically, you take the sum of x for group 1, square it, divided by the sample size for group 1, then add the sum of x for group 2, square it over the sample size for group 2, and so on and so forth. And then here we take sum of all the scores, square it, and divide it by the total sample size, and that's how you would get sum of squares between. And sum of squares within is a little bit different. We square all the x's, all the scores, and then add up all the squared scores, and then subtract. This component right here on the right hand side of the equation is identical to the left hand side of the equation above, so you could just plug in the number there. So if you're interested in doing this by hand, you can watch the subsequent video. Alright, so in this table there's a couple symbols or letters that we need to understand. K is the number of groups, so how many groups are in our study. So our soda example, the K would be 3. N is little n is the group sample size, and big N is the total sample size for the overall study. So once you calculate sum of squares between and sum of squares within, you can calculate what are called the degrees of freedom. So the degrees of freedom for the numerator or between or effect is the number of groups minus 1. So if there's 3 groups, then we subtract 1, then our degrees of freedom here is 2. For error, the degrees of freedom is the total sample size minus the number of groups. So if we had 100 people in our study and there were 3 groups, then the degrees of freedom within would be 97. All right, this is where we get closer to getting our F ratio. We would calculate the mean squared variance for effect or between by taking the sum of squares between and dividing it by the degrees of freedom between. And we would get the mean squared error variance or within variance by taking the sum of squares within and dividing it by the degrees of freedom within. Then finally, we would have our estimates of how much error variance is in our design or our data and how much effect variance is in our design or our data. We would divide the within into the between, and that would result in an F ratio. And the higher that F ratio, the more likely we're going to be able to reject a null, but it is dependent on the degrees of freedom for the particular test. So if you're interested in doing this by hand again, you can watch the next video. All right, so that's been my brief conceptual overview of the one-way between subjects analysis of variance. I hope that it was helpful and enjoyable. If you're in my class and that wasn't enough to give you the conceptual background for ANOVA, I encourage you to watch the longer lectures posted on Blackboard. All right, thank you, and I hope that you enjoyed that as much as I did.